All right, good enough. So, our quiz next week, and I'll have this up again later. You don't need to copy this down right now. But so we want to be able to match slope fields, which we had to do in today's homework. Draw slope fields, which we did a little bit yesterday. You're going to do more of that today. Sketch a solution curve, which is really easy. All that means is you have a slope field, and you just kind of give you an initial condition. You put your dot in there, and you just go with the flow. You just follow the slope segments. So that, and then Newton's law of cooling. Now, I'll be honest, there was not nearly enough work shown on number 23, or maybe even 24, mostly 23, for all the stuff you had to do there. I mean, you know, the answers were in the back, I know, but there was a lot of stuff to do. That 23 probably should have had half a page worth of stuff on your paper, right, when I'm going around looking at your homework. I know you do most of the lot on your calculator, but remember, as we've said all along, you know, you've got to write down what you're doing, write down those steps and so forth. So, you know, if you had 3 or 4 lines of answers, that would not nearly be enough. Now, you know, that's just the homework. Hopefully you understood where those answers came from, and you'll be able to do that on the quiz, right? Because we probably won't do much of that between now and the quiz next Wednesday, other than we will on Tuesday, we'll do some review problems. You'll get a chance to work that again. But Newton's law of cooling is pretty straightforward. You're just plugging numbers into this equation. You just got to make sure you know this equation, you know, and you've got it. So, all right, and then we're going to get into limits starting tomorrow, and we're going to be working on that. Okay, so let's talk about the first few problems, 3, 4, 5, 6. Those were all pretty much the same exact problem. Okay, they was it 3 through 6? Did we do 3 through? We did 3 through 14, right? We did all those. Okay, so let's just pick one out here, like number 4. Okay, so number 4 says, suppose that, I mean, it was a lot of fancy words and all a bunch of stuff, and it was really, there was not much to it. But the point is, you can read the fancy words, you know what everything means, and you can make sense of it, right? That's the key. So it says, suppose that g of t is a solution to this differential equation, y prime equals y plus 2e to the negative t. Now let's just talk about that a second. Does that, did I get that right? Does that bother anybody that there was g here and there was y here? Or did that even dawn on you that that was not a connection? What do you think? I mean, it's okay if it didn't bother you, but do you understand how really, normally, if g is isn't it the original function? So this should have been what right here? Or could have been g prime, and then this be g. But the difference is, when we use f, I mean, just traditionally, when we use f and we use g and we use h for functions, we usually write it f of x, g of x, h of x, f of t, g of t, h of t, right? We typically write like that. When we write y, for some reason, we don't usually write y of t, which we could, though, right? I mean, we could. It just, y is the output, just like g or f. So a lot of times what you see, and you've seen this all the way back to Algebra 2, is a lot of times you'll see in the problem y equals g of t. And they're just saying that those two are interchangeable, and you can use y or you can use g. So that's kind of understood here. I don't really like that because I would rather they would have said in the problem, I wish they would have said, suppose that y equals g of t is a solution. I wish they'd have connected those two. I think that would have been better. But it's safe, I guess, here to assume that. Okay? But, so y is the solution, or g of t, either way. Then it says, and then it says g of 0 equals what? What did it say there? G of 0 equals 1. It said, show that y equals 3t plus 1 is the tangent line at the point 0, 1. right? Or explain why or whatever. Well, I just think show the work. I just think if I was doing this, I'd say, well, I'm just going to find the equation of the tangent line, and it better come out to be that. And which we talked about the other day, right? How do you find the equation of the tangent line? What should I write? As soon as I read a problem that has anything to do with equation of the tangent line, almost every time I see the words equation of the tangent line, I'm going to write down what? What am I going to write down? Y equals, I don't even write the M usually, but I leave a space for it. Now in this case it's supposed to be X, but it's T, so I'm going to go T minus blank plus blank, right? I mean, maybe we should all chant this together. I don't know. I don't know what will get it into our head. But when I read the words equation of the tangent line in a problem, I'm going to write that down. I'm going to write that down. Because it's probably wanting me to find the equation of the tangent line, or it's saying to show that this is a tangent line. And maybe it gives me the equation of the tangent line, so then I wouldn't have to do that, I guess. But if it's saying anything about find or show or explain why the equation of the tangent line, or use the equation of the tangent line, I'm writing that down. Okay? Every time. So what goes here?
0.
And what goes here? Slope. Right? How do you get slope? You got a differential equation, which has a y prime in it, which gives you slope. So, I'm going to put a 1 there. Now, you're supposed to explain why it is, so you better have this on your paper, right? You better not just put a 3 there. You better show why there's a 3 there. So you better show on your paper that you have plugged in these numbers. So you got y plus 2e to the negative 0, right? Like that. And that's going to equal 1 plus e to the 0 is 1, 1 plus 2, which is going to equal 3, right? So y prime equals 3, so now I can put a 3 there, so I get y equals 3t plus 1. Sure enough, it's almost like that T-chart problem, right? Okay, I just showed that the equation of the tangent line is 3t plus 1. So on 5, when they say find the equation of the tangent line, just do that. On 6, they say, you know, is this an equation of the tangent line? You know, and on 3 they said explain why, like 4. So, but they're all the same problem. It's just the idea of getting into your head that, hey, you got a differential equation. That's a way of getting the slope. Difference is it's got x's and y's in it, maybe. It looks different than just when we do a chart problem, we just do the derivative. You know, that's it. Okay, now, here's your 8 graphs. So let's talk about this matching. So this is 7, this is 8, this is 9, or no, this is 10, this is 11, 12, 13, and 14, I believe. Okay, so you're going to do some more of this today. You're definitely going to have to do this on the quiz next week. This should be the easiest part of the quiz, right? Problem with matching is if you get off, and you can miss a whole batch, you can miss 8 problems here, right? Now, typically people aren't going to, and it should not happen because it's not that hard of a concept. Okay, so when I'm looking at all these different slope fields, let's review what I did yesterday. Now, Emily and I were just talking this morning, so let's start out this way. Let's start out the longest and slowest way that there would be to do this. So here's the first one. This is Roman numeral 1. Y prime equals 2t. Okay, all we can do is plug into this to get some slopes, and that's how we would do this, right? Well, let's just take a point like this one right here. Has the point. This is the point 2, 3. Looks like to me. This blue dot right here. 2, 3. Okay, so let's take the point 2, 3 and let's plug it in and let's see what we get. Well, all we can plug in is a 2 because we just have a t there. So 2 times 2 is 4. Okay, so is that a slope of 4 right there? No. So let's go on this one up here to 2, 3. Does that look like a slope of 4? Oh, I should go across here. Let's go up here to 2, 3. Does that look like a slope of 4 right there? Maybe. So that's a possibility. And then I go over here and I go, hey, is that a slope of 4 right there? Well, maybe, right? Maybe. Looks pretty steep. Is this one a slope of 4 right up here? No, that's negative. No way. Okay, and so I could go through there and I could eliminate some, right? And then I could say, okay, I've narrowed down to this one and this one, whatever. And then I could pick another point, right? right? Pick another point. Then process of elimination, I can come up with it. Now, it can take a long time, but it could work. Now, if I'm smart about it, then I start saying, well, okay, if I'm only plugging in a 2 in for t, then I wouldn't even have to plot this point, but I could try all of these points right here, right? All of these points here have a x value of 2, right? So all of these better have a slope of 4, right? If I put a 2 in for t. So then I start realizing, well, this one looks like a slope of 4 here, but down here it doesn't, right? So when x is 2, this is changing, right? So I already eliminated this one, but look at this one, all the way up and down there. I'm getting a slope of 4. Does that make sense? So this is what I was trying to get across to you yesterday, is if you have a column where the slopes never change, like here, it looks like the slope is 4 whenever x is 2, then that means that that differential equation is only affected by the x value. The y value, when you go up and down here, the y value is changing, right? When you go up and down, the y value is changing, but the slope never changes. So that means the y value doesn't affect the slope. If the y value doesn't affect the slope, that means the y is not in the equation, right? Only x. So if you go up and down, and I don't know how you remember that, I guess maybe a vertical line is x equals. Is that a way? A vertical line is x equals, right? So if you have vertical columns where the slope never changes, I don't know, it's only going to have an x in it or a t. Okay, so now, if we do it that way, then I could take this problem, Roman numeral 1, I say it's only got an x or a t in it. Well, it could be this one. Where's another one that's got only columns? This one? Those are the only two? Those are the only two that have columns where the slope never changes. Okay? So, all I got to do is pick a point like 2, and I get 4. Here I pick 2, and it's definitely not 4. It's not steep enough. So I know this has to be Roman numeral 1. Right there. Right? So that makes things easier. Now, what was the next one? What was Roman numeral 2? Y prime equals negative what?
2t.
Negative 2t? Oh.
There's more answers in Roman graphs. Yeah, there's 10.
Oh, there's 10 answers. I got you. Okay. So negative 2t has got to have columns, right? Like this. So, yeah. So the other option, though, the only other option it could be is this one, and there's no way it's that, right? It's negative 4. So you know, okay, so we're not going to use that one, right? We're not going to use that one. Okay. Or, okay, so now, so did any of you do it backwards? Did you just look at number 7 and then go through the list and try to find it? Okay, so let's talk about that. That would be an option as well, and you can do it either way. So now you look at this one. So let's do it that way. So let's say you start with number 7, and you say, all right, if I go up and down here, oh, the slopes are changing, right? But when I go across, what do you notice? So what's that mean? There's no x in the problem. There's just got to be y in the problem. Because whenever I go across, the x is changing, but the slope isn't. So there's no x in the problem. It's got to be just y's. Okay, so now I look through my list that just have y's in it. And let's take one of these points. So let's take this point right here. Again, 2, 3. But we only have y's in the problem, so let's just put a 3 in, right? So let's find all the ones that just have a y, and let's put a 3 in. Cosine of 3. Well, 3 is like pretty close to pi, right? 3.14. So what's cosine of pi? Negative 1. So does that look like negative 1? Looks like it could be. Okay? Then let's go down to 1 minus y. 1 minus 3? Negative 2. Does that look like negative 2? Maybe. Looks more like negative 1 to me. Are those the only two? Oh, 10. So put a 2 in, and then 1 minus 2. Or no, we're putting a 3. 3, 1 minus 3 is negative 2. 3 times negative 2 is negative 6. There's no way it's that steep, right? So now, I might be convinced that this has to be Roman numeral 7, but I might want to pick another point. So maybe I'll pick this point right here. What's the y there? y there is 0, right? So if I go back to Roman numeral 7, cosine of 0 is 1. Look like a 1? Yeah. Okay, and then let's do Roman numeral 9, 1 minus 0. Oh, God, that's 1. Well, that didn't help any. Okay, what about down here, like negative 3? Let's try that. And that'd be a y of negative 3. So cosine of negative 3, that'd be like negative pi. What's cosine of negative pi? That'd be over here. That's negative 1. That looks reasonable, negative 1. And let's put negative 3 into Roman numeral 9. 1 minus negative 3. Be 1 plus 4. Oh, okay, there we go. No way. No way. Right? So it's got to be Roman numeral 7. Right? It's got to be that one. So process of elimination, that's how you're doing it. Okay? Now, we have 2 others there. Roman numeral 9, Roman numeral 10 only had y's in them. I mean, if I was doing this, I'd probably go and try to find the ones that only have y's. Here's, this only has x's. This one only has y's in it. Right? Is there another one? This one. This one only has y's in it, right? Because you go across. Again, sometimes I think that way. It's horizontal line. Think like horizontal line is y equals, right? So if I can draw a horizontal line through there, I think y, it only has y's in it. So if this has a y of 2, okay, so let's try third. I think I would skip around a little bit. I don't know. Since I just did those ones with y's, but it doesn't matter. So Roman numeral 9, Roman numeral 10 I'm thinking about. So I'm going to put a 2 in. I'm going to put a 2 in for y in Roman numeral 9. 1 minus 2 is negative 1. Does that look like negative 1? Looks a little steeper than that. But let's try the next one. Let's put a 2 into the next one. 2, and then 1 minus 2 is negative 1. That's negative 2. That looks a little better. I guess we could compare these two. Look at this one at 2. This one isn't as steep as this one isn't. Again, we could go to some other points. We could go to 0. We could go to y of 0. Well, here these are definitely different. We go negative 2. Look at these compared to these. So if we go negative 2 on 12, 1 minus negative 2. If we go to Roman numeral 9, 1 minus negative 2. That's 1 plus 2. That's 3. Definitely not this one because those are negative. So this one has to be Roman numeral 9. And this one has to be Roman numeral 10. Would you agree with that? Okay. Got to be that one. Okay. And then this one has just, we said 11, just has x's in it. So what's another one that just got x? We ruled out 2. Sine t, it's the only one left. Roman numeral 8 is the only one left, right? Sine. So if we go here, like if we do an x of 0, sine of 0 is 0. If we go over here, pi would be right in here. Sine of pi is 1, and so that could be reasonable. No, sine of pi is, wait a minute, what am I doing? I'm putting in x's, okay? So if I put in an x of 3, why is that not looking like 2? Is that what you had for 11 with Roman numeral 8? That doesn't look right, does it? If you go right in here at 3, it's that right there, right? What am I missing something there?
So you're putting in a 3 for
I'm putting a 3 in for x, which would be right here. So let's call it pi. 3.1. Sine of pi is 0. So the slope should be 0. Right? that now?
Just opposed to it.
Well, 3, but I'm rough, but 3, 3.14 would be just past it. I'm saying nowhere here around 3 does that line look like it's slope of 0. Does it?
Why are you up 3? Plus,
Well, I don't, it doesn't matter where I am here. It all along here is an x value of 3, right? All of these points are an x value of 3.14, let's say. See what I'm saying?
isn't sine of 4 should be negative 2?
Well, yeah, once you get past pi, sine's negative. So once you get past 3, this should be going back down. I taught out of this book for 10 years. I guess I haven't looked at these problems that closely, maybe. Is that what they have in the back?
There's some other, they have it at 8.
I've never looked at this one this closely, but I just think they have it mismarked. I think they have it mislabeled. I think this should have been, to me, this should be like 1 and 2. Because it looks to me like it gets the steepest right in here, where my line is, and then it's starting to level off. Well, where would it be the steepest? Where is sine equal to 1? Pi halves, which would be 1.57.
Yeah.
So to me,
It's not.
yeah, to me, this should be 1 and this should be 2. And then at about 1.57, right, you would be getting a slope of 1 right through here, which is what it looks like. And then this would be 2, and start to level, and then at 3, it would be back to 0. I mean, we can do an antiderivative of this one. What's the antiderivative of sine? Negative cosine, right, would be the antiderivative. So we should be looking at a negative cosine, which would start down at a low point, go up, and then right. I mean, that's what it would do. I just, our labels are off here. I can't believe I never noticed. I guess I've probably done a few examples, and then we've moved on. Today we just looked at it a little closer. There's just no way. Yeah, if you go from 2, of course, the problem with doing it on a calculator is this has so many more slope segments than your calculator has that it's hard to compare sometimes. But yeah, there's no way those labels are right. There's no way those labels are right. If those were 1 and 2, it would make more sense. It would make more sense. Okay. All right. The y doesn't really matter. All right. Or even if they were 1, 2, 3, I mean, well, still the steepest part of it should be when it's 1. The slope should be 1 at pi halves, so at about 1.5. So that's interesting. Well, I'm curious to see now if the other class caught that. Probably had some people in other classes who caught that, but never said it. Didn't want to say it. But okay, so the ones that are left. So that was Roman numeral 8. Is that right? Okay. So the ones that are left, these 3 all have both, if you go vertical column or you go, we did that one. Vertical column, they change. Horizontal row, they change. And so that means they have to have both x and y in them. And so then you just go ahead and you just pick some different points. Like, for example, this has a negative slope, like when x is 1. Here, when x is 1, you got a positive slope. Here, if we were going to do the point 1, 2, here you get a negative slope. Here you get a negative slope of 1, 2. So that'd be pretty easy. So if we just just pick a point, right? Just pick a point, 1, 2, and try it in all those other ones, and you see what's what. Well, I think it ends up being for 9. They say it ends up being Roman numeral 3. For 10, it's Roman numeral 4, and for 14, it's Roman numeral 6, right? But it's just about plotting points and then checking the slopes and getting the match. But you can speed up the process if you kind of do this thing with your horizontal and vertical columns. Just an X, just a Y, whatever. Okay, now, other thing that we talked about in here was sketching the solution curve. So, if that is, let me see, okay, so sketching the solution curve just means I give you an initial, now all these blue dots are separate curves. All the blue dots would be different, and you were supposed to do that, but they said to sketch it, but that'd have been hard to do. I didn't really intend for you to do that. So like right here, if I was going to go through this initial condition, this looks like it comes down here, it would level off, come back up, and then it looks like it comes in here. Now I would say there's an asymptote right there. Anytime you see you get a bunch where it's horizontal for a long time, where you get zeros for a long time, that's typically a asymptote. And so probably what's happening is this one, it probably goes below here a little bit, but it would level, it would come back up, it would follow these curves, and it would probably do something like that. It's probably what you have going on there. But if we were starting at this one, let me do that in red. If this was my initial condition, then it would be down here, it would be this branch, it'd be up here. And then it's coming up here, it looks like it's leveling, and then it's coming back down, and then I'm just following those lines, and it looks like it's something like that. Okay, if I was doing, let's do black for this one, if I was on this initial condition, it would follow and come in here like so, and then it would come down here like that, and then it would follow, and then it would do something like that. So if I give you an initial condition, be able to draw in reasonably well the solution curve and follow those points like that. Okay, this one again would be one where it would be coming down here like this, and then it would be flattening out, and then that looks like kind of an exponential kind of there. Okay, this one you would probably have a situation where it would be going up with a vertical asymptote coming down here, and then having a horizontal asymptote like that. Okay, so we call those branches of the differential equation. So this solution would be a branch up here, whereas if you had this initial condition, you would be getting this piece down here, right? You would have both of these as a solution. These are each individual solutions based on the initial condition. Okay? All right, so that's good enough for that right there. All right, let's move on to number 23. I want to go through a little bit of this with you because again, you did not. I like this problem because it really takes you through the different things you can have. Anybody know who Boris and Natasha are? Did I tell you that yesterday? But you ever seen the cartoon Rocky and Bullwinkle? The moose. The moose. Yeah. I don't know if we can find it. That's Boris. From Rocky and Bullwinkle. Just a little. Classic cartoon. Anyway, so that's who they're talking about. But so basically what you have is you have two different containers, right? You got a cardboard, it's better for the environment, or you got styrofoam, which is worse for the environment, but keeps your coffee warmer. So they have different K values. Okay, how long does Boris's coffee stay above 70? How about Natasha's? How hot is each cup after 5? Then they have you redo those based on those. So I'm going to walk through. I'm going to do this a little bit like some of you seems like did your homework, which is just in bits and pieces. Okay, but if we did a quiz problem on this, make sure you do it. So again, of course, everything starts with this. Okay, so this is the last time we'll kind of extensively go through Newton's law of cooling. So make sure you've got the idea. But first and foremost, you just got to know that, right? You just got to memorize that. Because I'm not going to give that to you on the quiz, right? If there's a problem that deals with cooling, you're going to have to know that's the equation I want. Now, the differential equation is this, right? But that's not nearly as useful. You don't really need to know that. I might give you that in the problem. I might give it to you as a differential equation, which would tell you your K value probably, tell you your T value. Or I might just do it like this problem where I just tell it to you in words, right, what the temperature is and so forth. Now, it's nice it gave us the K value. So if we're doing Boris, right, his equation is going to be Y equals, and what's the room temperature on this one? -10 because they're outside and frostbite falls, plus AE to the, and then Boris's, his is -0.05 because he doesn't care about the environment, right? So that's his equation right there. And Natasha's equation is y equals negative 10 plus AE to the negative 0.08 t. Now they both have the same initial conditions, right? Y of 0 is 90. We don't need any other information because, like the problem we did yesterday, we had two pieces of information because we already know K, right? We already know K, so A is the only unknown thing, right? So we put a 0 in for T and we get 90 out here. So we get negative 10 plus AE to the 0. So A would be what? 100, right? Because you get A and then you'd add 10. So now Boris's equation is negative 10 plus 100 e to the negative 0.05 t. So once you have that equation, you can answer any question you want, right? And they asked two. They said, how long does it stay above 70? So let's get logged in on our calculators here. And of course you can't log in just yet. Yeah, you can. And the winner is Skylar. Okay, so let's go through the solve one more time. So we're going to solve that equation. Now, you guys did a good, who was our presenter yesterday? Max, and we didn't give Max enough credit yesterday on this one, and we'll show you what in a minute. So we're going to solve the equation. So what was the equation we had? We're going to solve this equation, except we want to know how long it stays above what? 70. So we put 70 where? We put 70 right there for the y, right? And we're going to solve that equation. This you will need to be able to do on your calculator. You will need to be able to solve this. That's about all you're going to need your calculator for in this quiz, really, is going to be a very short calculator part on this quiz, okay? You're going to need your calculator to solve the equation. I'm sorry, you didn't have time to write it down. There we go. Yeah, there we go. I need decimal point. Put a decimal. Yeah, there we go. Okay, so you get that thing, it said missing argument. What did you forget? Comma x. Except not up there. There you go. You got the equals. A lot of times when we do these, we do the derivative, set it equal to 0. So a lot of times when we do solve, we're setting it equal to 0, right? But here we're saying equal to 70, but we have to do comma x. So, but we need to know that, right? If we get that error message on the quiz, it says not enough arguments or whatever, you got to know that's what we're doing. So you're solved. Okay, so Max kind of went through that yesterday, and we didn't talk about this. I didn't think about it until second block class screwed it up when they were presenting, okay? So there it is. So what would be the answer you'd put on your paper? 4.463 would be a good answer right there. 4.463. So that stayed above for that many minutes. Okay, now let's go down here to this one. We would have the same 100 degrees. So Natasha's equation is the same thing. Okay? The K's, yeah. Because when you put in a 0, they have the same initial conditions. So the A is going to be the same because that's based on the 90-degree starting temp. So now we're going to solve this one with a 70 put in there. Okay? So now we just chat. Good job. Just copy and paste. No sense to it. And look at that. That makes a big difference, doesn't it? Now it only stays above 100, 2.789 minutes. Okay? Now, the other question was, how hot is the cup after 5 minutes? What do you do there?
Put it 5
You put a 5 in for the time. Now this is the one that Max just deftly handled. We, again, got to give him credit. And kind of putting Skylar on the spot, but don't worry, the other class kind of goofed this up. So now, Skylar, you put, and let's go to the top one, let's put a 5 in for the X. Let's put a 5 in for the T. So how do we type that in? Do you change what? No. Well, yeah, right. We're not doing, okay. Yeah, I'm sorry. Let me go back to this. Okay, so what we're doing is we're taking this equation right here, right? Yeah, the 70's not part of this now. We're doing this equation, and we're putting a 5 right there for T. Right? So think about how you would type that. Everybody, think about how that, and go ahead and do it on your own if you want. Okay, think about how you type that in for T. See, this is what made me think of this, because this is what the other class did yesterday. What's going wrong right here?
Did you just put a 5 in? Like, do you mean the equals? Just put
Jesse say that.
You don't need to solve for the complex.
You don't need the vertical bar either, right? You only need the vertical bar if you were going to keep the X here, and then vertical bar, and then X equals 5. But now see, I blame all your other math teachers for this, for that confusion. Because here's what we don't do a good job of. We don't do a good job as we go through the years of really teaching you the vocabulary of what's going on. Most of you think solve just means get the answer to any problem. Is solve, right? What is solving to the calculator? What do you solve? An equation. An equation is something that has an equal sign in it, right? We're not solving an equation here. We were in the other part. We were doing 70 equals da-da-da-da-da with a t here. We need to solve that for t. That's not what we're doing here. Now we're trying to find y. Y equals this. All we're doing is trying to, and what's the word? It starts with an E. No, well that is, this part right here is an expression, not an equation. And what do you do to an expression? You evaluate it. You find the value of it. So we're trying to find the value of this. So we're evaluating an expression. We're not solving an equation. So in the first one, we're putting a 70 in here for y, and we're solving that equation. Okay? And so that's why we needed the solve. But in the second one, we're putting a 5 in for t, and we're just evaluating that number. So we don't want the solve. Now, if you wanted to put an x there and evaluate that with x equals 5, then you could put the vertical bar and do that, right? Okay. So, and that's important, obviously, because you're going to have to be able to do both on your calculator. So when Newton's law, so that says that, now grab that and change that. Grab that and change that 0.05 to a 0.08. And what did this number mean? What's that 67.88? After 5 minutes. So his coffee's down to 67.88. Hers is all the way down to 57, right? Because she's got the styrofoam, or she's got the cardboard cup instead of the styrofoam. Okay? So those are the temperatures after 5 minutes. And then it says, what if they go in the store? What would that change in the equation? The negative 10 would become 25, which of course that changes what other number? The 100 will change, right? In other words, you got to start over. So now you've got 90 equals 25 plus a e to the 0. So at times 0, you have a temp of 90. Well, e to the 0 is 1, so a would be 90 minus 25 would be 65. So now your equation for the next set of problems would be 25 plus 65 e to the negative 0.05 t and negative 0.08 t. So now your equation changes. So when the big T changes, the surroundings. So it should cool slower, right? Right? It should cool down slower because it's now in a warmer environment. And so now, but again, changing that T then changes that A as well. So you got to kind of go back to the beginning and put in your initial condition and answer those questions, okay? There's really no calculus in any of that right there, right? The calculus is this solution comes from this differential equation. It's just about plugging numbers into an equation and getting answers out. Either solving the equation for the T value or evaluating the expression with a certain T value. So very important to understand the difference there. Okay, and then 24 was just another problem. And again, you could look, that was even. It said, they give 30.53 minutes. I don't know if they didn't go to 3 decimal places with it. That was, how long does it stay above 100? So 30.53 is what they said. Okay, so just set it equal to 100 and go. But that's essentially your Newton's law cooling. Okay? All right, so I think for today we'll do one more day of just kind of this idea, especially the slope field thing. I've got is everybody logged in? Because thank you, Skylar, for doing that. All right, I want to send you this document. I lost it there, I guess. Oops. Okay, so did you get that? All right, so you can open that up. Now, I got 2 different worksheets for you today. Should be 3 pages on this one if it all stapled properly. Okay, so let's talk about this one first. So on this one, you've got some slope fields to sketch, so that's going to take you a fair amount of time, so I'm going to give you some work time today. On the second page, if you turn to that, I want to caution you a little bit. When you turn to the second page, there's some matching on your slope fields. Now, the difference here, though, is that look at the equations down here. What do you notice? It's not the differential equation you're matching it to. It's the y prime. Now, that's not what we usually do. We usually match it to the y prime. This would be easier because when you look at the slope field, remember we can kind of see the parabola? If you look at a slope field and you can kind of see the parabola in there, that's the y equation. So if you look at one of these and you can kind of see the parabola, well, that's going to be the x squared. Right? You know what I mean? So it's going to be an easier match. You're not going to have to plot points and calculate slopes and stuff like that. Okay, go to the last page. The last page is a more common and probably what I'm going to give you more on the quiz. And that matching is where you've got the 4 pictures and then you've got the different differential equations where you have to actually plot points in there and match their slopes on the slope field. And then there's a couple here where they give you the slope field and they just want you to sketch the curve in there. So that's not going to take you very long. So the front page is going to take you the longest. So if we look at number 1, for example, let's just do number 1 together. Okay? So, because we did one of these together yesterday, but now we got one more. So remember, dy over dx is the same as y prime. So it's just y prime equals x plus 1, same thing. Okay? So if x is 0, what do you got? So what's that mean? On the y-axis right here. So if x is a 0, which would be here, 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 and here. All the time when x is 0, you're going to get a slope of 1. When x is 1, you're going to get a slope of 2, so that's going to be steeper. But again, there are these vertical columns, right? So same x value. When x is 2, you're going to get a slope of 3, which is steeper yet. And it's hard to make them really consistent. And then when x is 3 out here, you got a slope of 4, which is really steep. So then, at that point I draw them almost vertical, but whatever. And so then you go to -1, well now you got a slope of 0. So, and then -2, that'd be a slope of -1. It's not going to surprise you, this one's actually going to look like what shape? And then at -1, 2, 3, -3, you're getting a slope of -2, so it's going to be steeper. And it's got that look of a parabola, right? Well, that makes sense, because this is one of those we could do the antiderivative on. This would be 1/2 x squared plus x plus some c value, which we don't know, right? So there could be some, but don't worry about that. But that should go through your head, and that'd be a reasonable thought. Okay, so that's a pretty easy one to draw. So if you just have an x or just have a y, they're pretty easy to draw. When you have an x and a y, they take longer because you have to plot each individual point. It takes a while. All right. So that document I sent you is with this worksheet. And so you just follow the directions on this worksheet. You go through the pages on there. Now, when you go through the pages on the calculator document, it's going to have places for you to type in answers on the document. You don't have to do that because it's the same questions they're asking you on the paper. So they ask you these questions on the paper to calculate these slopes or whatever. And there'll be a place on the calculator screen where you can type those in. You don't need to. Just put them on your paper, right? Answer them on your paper. And then there's a matching exercise on the back. And they do tell you that you can go on to page 4.2 of the document and you can actually type these in to look at them. I would not bother doing that. Just check using that page. I wouldn't bother doing that because you're not going to do that on the test. On the quiz, you're just going to have to match without a calculator, right? So I don't think graphing them on your calculator and looking at their slope field is anything of really much value. So I don't worry too much about doing that. Just do a match. So you got a lot of practice with matching today, little practice with drawing, and so forth. Okay? So you can have the last half hour. That's it. That's what we'll do. Okay? Make sure you can do Newton's law of cooling. If you didn't spend a lot of time on 23 or 24, go back and practice that. But that's the main thing. Then we're going to start on the next thing tomorrow, which is probably the harder part of the next week's school. So we got to make sure we get some days in. That's going back to limits.
Could I take that now?
No. It seems to me, I didn't say that, but yeah, it's got to be on. We take that one in class.